We're going to start with the end of chapter 4 and the definition of congruence. Two figures are congruent if and only if one is the image of the other under some isometry. So the isometries, remember, are the idea of reflections, translations, rotations, etc. The symbol for congruent looks like an equal sign with a curve or a similar thing above that. So two figures are congruent if one reflects to the other or matches an isometry. That's something that we talked about, or we will talk about in chapter 4. So then we go to section 5.1. The main thing in section 5.1 is the idea of corresponding parts and the CPCF theorem, the corresponding parts of congruent figures. If two figures are congruent, then any pair of corresponding parts are also going to be congruent. So if we have a triangle ABC and a congruent triangle XYZ, we would say that triangle ABC is congruent to triangle, and again we have to match up the parts, XYZ. So when you state figures congruent, you have to make sure you put them in corresponding order. By doing so, we can now say, by this theorem, that angle A is congruent to angle X. We can say that side AC, segment AC, is congruent to segment XZ. Congruent sides. So we've got three sets of angles and three sets of sides that are going to be congruent in the triangle. The ABCD theorem is the same one that we've been working on before. Now we're going to call it the ABCD theorem. Every isometry preserves angle measure between this collinearity and distance. Again, some of this stuff is kind of matching in with chapter 4. And then in section 5.2, those properties that we learned about equality are also going to be properties of congruence. So if you remember, a reflexive property said A was equal to A. We can now say something like angle A is congruent to angle A, or segment AB is congruent to itself, segment AB. The symmetric property is that if angle A is congruent to angle B, then we can say angle B is congruent to angle A. We can just flip them around. And the transitive property, segment AB is congruent to segment CD. Segment CD is congruent to segment XY. Therefore, segment AB is congruent to segment XY. And then we have these a couple of real simple formulas, or theorems rather. The segment congruence theorem, you can't say a whole lot with this. It is a biconditional, but this says, here we say that AB equals, remember that's an equal length. We're saying the lengths are equal, therefore we can conclude that segment AB is congruent to segment CD by the segment congruence theorem. But now it's a biconditional, so it goes in the other direction. The given could be that segment AB is congruent to segment CD. If that was the given, then we could conclude that AB equals CD. This is the figure is congruent, and now we're saying the lengths are equal. Again, that would still be by the segment congruence theorem. And then the angle congruence theorem is the same thing except for with angles. So if their measures are equal, this again says measures are equal, then we can say that angle A is congruent to angle C, and this is by the angle congruence theorem. It also is biconditional, so it works the other way. If we know angle A is congruent to angle C, then we can conclude that the measure of angle A equals the measure of angle C, again by the angle congruence theorem. I think that's it. Yep. Hopefully this helps get through at least part of this.